This is an example that shows the weight of astronaut as a centripetal force when he is in space station, as this shuttle is revolving. The question is, at what speed must the surface of the space station move so that the astronaut shown at point B will experience a push on his feet, and that push is equal to the Earth, his Earth weight. The space station is rotating. It completes its rotation at the point, comes back for a full cycle, the same as it was at the start of the rotation of the space shuttle. To solve this problem, you have to see only centripetal force acting on the astronaut. What is that? It is the Earth weight of the astronaut mg towards the center of the shuttle. And then by putting this into the equation, we're going to get the speed at the surface by multiplying the radius given the problem and the acceleration due to gravity. You're going to get an answer of 130 meters per second. This is an example on a banked curve or a banked road to be designed by an engineer in such a way that any car will move in this banked curve or banked road will not rely on the friction between the car and the road. In another sense, when the car is moving at a certain speed, this car will be able to negotiate the curve even when the road is covered with ice or even when the road is frictionless. Such a road is usually banked, which means that the engineer will take into consideration how to tilt the road toward the inside of the curve. And here, if the designated speed or the wanted speed of the road wanted to be 13.4 meters per second with a radius of 35 meters, what is the angle of the curve be banked? This is another example to uniform motion with the constant speed, a little bit difficult than the previous ones. Here, if you can see that the road at the bank has the weight in this direction downward, while the normal force, that is the force of this banked curve, is in this direction. This normal force will be decomposed into two components as theta between the normal force and the perpendicular to the radius. Theta is the same as the banked road. In this case, Fn has two components, one perpendicular to the radius or the circle of the car, if you like, and one towards the center, that is F sub n sine theta. Now, to continue solving this problem, you have by resolving the force, the normal force, to two components, one perpendicular to the radius of the circle, expected circle that the car is going to go through, which is this one, and the one along the radius, that's Fn sine theta, where theta is the angle between Fn and the perpendicular to the radius, which is the same as the inclined angle. In this case, you need to, from this diagram, you need to set up equations, and the most important thing is to choose the forces along the radius, where we have a resultant centripetal force is the product of mass and centripetal acceleration. So the only force acting on this car along the radius is Fn sine theta. By inserting this into the equation, having a minus sign, because as we said before, this force is directed towards the center, has a minus sign, as well as the acceleration, which has a minus sign because it's directed towards center. So then you're going to get equation 1. In order to get the angle of equation, you need to have another equation, and that equation is of the resultant force along the y-axis, or that one perpendicular, in another sense, to the circle. And as long as the car is not going up or down, so the resultant force along this axis, along the perpendicular axis, is Fn cosine theta minus mg equal 0, then Fn cosine theta equal mg. So these are the perpendicular forces. We have these two equations. We will solve them, divide one by the other. We will get tan theta equal v square over gr, and from here we can get theta is tan inverse of v square over gr, and this is the answer for the problem. If you substitute the values, you're going to get an angle of 27.6 degrees. This is if the wanted speed is 13.4 as requested. This is an exercise for you to do. It's again about a banked road, and the car is traveling with the speed v, and the given radius for the banked road is 28 meters, and the banked angle is 30 degrees where there is no friction. You need to find what is the speed of the car, and we'll follow the same method as before. The answer is 12.6 meter per second this time. This is an interesting also. It's about the plains highway and the way it's designed. If you can look at the airplane wings, the banked turn, and the lifting force of the plane is L in this direction, and in a similar manner to the banked turn, it has two components, one in this direction, one in this direction, and that is along the radius of the turn, and the component responsible for the motion is L sine theta, and obviously there is a component of L cosine theta in this direction, balanced by the weight in this direction of the plane, balanced by mg. And you follow the same procedure if you want to find what speed could the airplane make to make the turn on the highway and the high speed roadways of the airport.